So last week we started chapter 3, and we wanted to talk about the second law of thermodynamics. And the reason why we wanted to go through second law is because we want to figure out what will be the maximum work that a normal process can do. So at the very beginning of this chapter, we mentioned that for simple cases like if there's no work being done on the system, then based on the first law of thermodynamics, this is very straightforward. The change of internal energy is the change of heat, or the heat supply to the system. On the other hand, if you have an adiabatic process, which means that there's no heat coming in and out of the system, then the work will be the change of the internal energy with a minus sign, which means that when you do something onto the system, then there's a change of internal energy. But what if you're dealing with a process that is neither adiabatic and it's neither like without any work? So we wanted to figure out what will be the maximum work that a system can do during a regular process. So last time we mentioned that there's this process called a spontaneous process or irreversible process. For instance, like when you open the gate between these two chambers, the gas molecules of different kinds, they will mix with each other. And for a spontaneous process, once it reaches equilibrium, then it will stop. And we know that it cannot go back. So the system won't just automatically separate the two kinds of molecules. So this is, the first example is the mixing. And the second example is the thermal equilibrium. So at the very beginning, you have two separated systems, and they have different temperatures. And when you put them together in contact with each other, then the heat will flow from the high temperature system to a low temperature system. And then they will reach thermal equilibrium. And in that sense, the temperature will be the same. And this is also a spontaneous process, which means that the heat won't automatically transfer from one side to the other and then return to like the two systems with like two different temperatures. So eventually, when you put these two things together, they will have the same temperature. And so you can imagine that there are several types of, at least two types of spontaneous process, or you can say irreversible process. And we can also define a quantity that is sort of the measure of this irreversibility. And like I mentioned last time, the entropy, later we will define this, will increase in time, and eventually it will saturate. So you won't know like which way is before and which way, which direction is after. But at least right now, in this time of the universe, there's a certain direction of the growth of entropy. So we know that when we see this kind of evolution, we know which way is moving forward in time and which way is moving backwards. However, if you see something like this, then you don't know. So therefore, there must be a measure of this irreversibility. And to quantify the irreversibility, we use a term called entropy. And therefore, the entropy can be considered as the measure of degradation or the degree of irreversibility. And last time we stopped over here. We look at this example that when you have the same setup, a very similar setup as what Joel did for his experiment, that you have something mechanical that can transfer your mechanical energy into thermal energy, which is heat. And in Joule's setup, we know that when this paddle starts to rotate, it will heat up the fluid inside. Typically, it's water. And then you can measure the change of temperature because the heat is being absorbed by the water. Therefore, the temperature of water will be increased. And from that, he tried to calculate the correlation between heat and mechanical work, right? So that's how he conceived that the two things are the same. They are all energy, but just in different forms. But right now, what the textbook mentioned over here is a little bit different. So again, we have this conversion setup to transfer mechanical energy into, I would say, thermal energy. But over here, this reservoir, this heat reservoir is very huge. So the temperature is fixed at a constant temperature, which is different from Joule's setup. For Joule's setup, we want to see the temperature change. But in this case, in this example, the temperature over here is fixed. So therefore, in the next slide, I replot it this way, that this thing is actually a heat reservoir. So we can dump mechanical energy into this heat reservoir as a form of heat. So keep in mind that when you look at this example, the heat reservoir here, the water here, has a fixed temperature. Okay. So I don't want to go through this again. This is trying to say that when you release the wave, then the mechanical energy will be converted into heat or the thermal energy. So the interesting here is that the textbook mentioned this example, which he took from another textbook, I believe. And this example is a little bit hard to understand, but I will still go through this. So imagine that we have three different kinds of processes. And process 3 is the regular process that I just mentioned. You release the weight, and the mechanical energy, this work, will be converted to the heat or the thermal energy. And this thermal energy will be absorbed by the water here, or this heat reservoir. But this heat reservoir, this big tank of water, is kept at a temperature called T1. Okay? So imagine that this T1 it's probably better if you have a number in mind, so you don't have to worry about that. Let's say T1 is maybe, I'll say 20 degrees Celsius. And the textbook mentions that this process 3 actually can be divided into two processes. And that means we can divide this into like 1 plus 2. And process 1 over here is similar to the very beginning of this process. So you release the wave, and then the work can be converted into heat or thermal energy and will be dumped into the water over here. The only difference between 1 and 3 is that the temperature over here is higher than T1. So T2 is higher than T1. So imagine that here you have T2 at around, say, 100 degrees Celsius. And later on, after a short amount of time, this system will go through a different process, process number 2. And this process is a little bit, I would say, simple. The heat will be further converted or further transferred to another heat tank. And the temperature of the whole thing will evolve from temperature 2 to temperature 1, which means that you can imagine another heat reservoir is in contact with this heat tank, and then try to reduce the energy or you can say reduce the temperature of this heat tank from T2 to T1. Okay, so for process number 2, it means that originally the heat tank is at T2 and later it will become T1. So originally it was at 100 degrees Celsius, and after it was in contact with another larger heat reservoir, the temperature is lower to T1. So if you combine process 1 and 2, you'll see that it's eventually being reduced to process 3. Because if you combine these two processes, you'll see that you release a weight, and this process will transfer the mechanical energy into the thermal energy and being dumped into the heat tank, and the temperature will eventually go down to T1. So these two processes, 1 and 2, add together will become process number 3. So the essential idea over here is that process 3 is actually the combination of 1 and 2. And we know that this process is a irreversible process, because if there's no external force to put this back, and if you just release this very fast, this is an irreversible process. So during this process, you know that there is some certain degree of irreversibility being produced. And we know that 1 plus 2 equals 3, and we know that the irreversibility, the quantity that we want to define, should be consistent. And if you have the irreversibility of 1 and that of 2, if you add them together, it should be the irreversibility of number 3. And we know that, therefore, irreversibility of process 1 will be less than that of number 3. Is that okay with you? So the irreversibility over here is less than the irreversibility over here, because the temperature is still higher, so it has a higher possibility that you can reverse the process. Okay? And the argument in the textbook is that if you can divide a process into 2 processes, then each one of these will have a smaller irreversibility while comparing to the original one. But in fact, what we're interested in is only this one, 1 and 3. And if you look at the ratio Q over T2 and Q over T1, you'll realize that this is greater than this one, because Q is the same. The heat being converted from work into, say, thermal energy is the same for these 2 processes. They're all both Q. But the temperature for this one, it was kept at a higher temperature, T2. And this one, the original one that we consider, is at a lower temperature. So it's harder for this one to go back to its original state, because the temperature is already lower. So if you use this ratio, you can easily define a quantity that is larger in the case of 3, but is smaller in the case of number 1, right? So this seems to be a good measure for the irreversibility. And because Q is the same and temperature is different, and T1 is smaller than T2, therefore Q over T1 is greater than Q over T2. And this simply states that let's say this is actually the entropy. The entropy change of process 3 is greater than that of the process 1. So this is consistent with what we want. We want a measure that can quantify irreversibility. So I won't go through this again. These are just the words stating on something that I just mentioned. And therefore, the quantity Q over T is taken as a measure of the degree of irreversibility. of the process. The value of Q over T is called the increase in entropy. So please bear in mind that this is a difference. This is a change. So we are not stating that this is the definite value of entropy, but this is the change of entropy. So to be more precise, we can write this down. I think on the next slide we have that. But here you see that we define, say, it actually should be written as delta S as Q over T. But this is also a difference, right? This is the energy that you absorb. So in reality, or in some cases, you want to write delta Q over T. But typically, when you write down Q, it's already an amount of change. It's a heat change. So this is also a change in terms of the energy. Or in terms of ds, you write dq over t. Or in the textbook, I think it's delta q over t. It depends. So you'll see different kinds of notations. You'll see different kinds of notations. But please bear in mind that based on the argument that we went through, we're defining the change of entropy rather than its absolute value. To talk about the real value of S, we have to go to the statistical thermodynamics. But in the classical thermodynamics, we only define the difference of entropy. This means that at a fixed temperature, if the heat is going into the system, then we can measure the change of the randomness of the system by using this ratio. Okay? So again, when heat Q is absorbed by the system at a constant temperature T, the entropy produced by the system, delta S, is something like this. So originally, the system must already have some randomness, but by absorbing this heat, then it becomes more random. So the change of that randomness, delta S, is defined as Q over T. So this is similar to what I just wrote. Delta S is Q over T, or you can say delta Q over T. And ds, if you want to write it as a differential, it is dq over T. And this is this example over here will help you understand more clearly. Like if you have a microscopic view of particle movement in mind, then you can imagine that a bunch of gas molecules, they are confined in this box, but at the same time they're in contact with this heat reservoir. And let's say that the temperature over here was capped at 0 Kelvin. So it is very close to, I'll say, 0 temperature. Therefore, there shouldn't be any large movement of the particles within. So you can imagine that it seems that these particles are almost not moving at all. And on the right-hand side, you have a different system. Well, I'll say it's the same particle system, but with under different temperature. So the heat reservoir here is capped at 300 Kelvin. So the temperature is higher, and we know that because the temperature is higher, the particles inside is moving around more rapidly, and you have more random actions. Imagine that they all absorb, and both of them absorb the same amount of heat, delta Q, from the heat reservoir. And again, if you absorb heat from the heat reservoir, the reason why we call this heat reservoir is because the temperature is fixed. So imagine that heat is transferred, but there's no change in terms of temperature. By adding the same amount of heat into the system, we know that from the left-hand side, because originally there's no movement at all, so this heat will change the particle movement by a lot. So the randomness will be increased by a larger amount in the left-hand side system while compared to the right-hand side. Because for the right-hand side, these particles are already moving around very rapidly and in a random fashion. So even by adding a the same amount of heat or thermal energy into the system, there's no big change. So in terms of microscopic view, we can understand why, in this case, the change of entropy is larger for the low temperature system while comparing to the high temperature system. It is because for the high temperature system, the system is already very random. It has a lot of random motion for these microscopic particles. So by adding the same amount of heat into the system, there's no big change on the right-hand side, but there's a huge change in terms of randomness for the left-hand side system. And again, this is at a lower temperature, this is at a higher temperature. So this is consistent with what we define over here. The same amount of heat is being supplied, but if the temperature is different, you have different change in terms of randomness. Okay, so if you go through the textbook and it seems that the argument is hard for you to understand, you can come back to this microscopic view, which might help you, I think will help you understand it more clearly. So next we're going to define processes. Although we've already mentioned several things about irreversible process or the spontaneous process, but what we really can do is actually the reversible process. I say can do is because for all the calculations that we want to calculate in the textbook, they are all reversible processes. For irreversible processes, they are hard to calculate because you don't know how much heat or how much waste heat will be produced during the process, unless the problem tells you like how much waste has been produced. Otherwise, it will be hard to calculate just from the state functions. So here we want to go through reversible process again. The degree of irreversibility is 0 for the reversible process. It means that there's no degradation. And at all times during the process, the system is at equilibrium. So for instance, in the case that we just mentioned, we release the weight over here. When we release the weight and the weight is starting to drop, then there's a break in terms of equilibrium. Therefore, this is an irreversible process. However, if we move the weight downward a little bit at a time, then we can say that at each moment, the system is at equilibrium. So there's possibility that this process can be reversible. Therefore, a reversible process means that at all times during the process, it is always in equilibrium. Then it means that we have to take a very, very long time to finish the process. And a reversible process takes a system from state A to state B. It's one in which the process path passes through a continuum of equilibrium states, which is the same statement as in the point number 3. So an actual process can be considered reversible only when the influence, for each step is very, very small. Or in terms of calculus, we say this is infinitesimally small during, and you have this kind of small driving force, such that during the process, system is never more than a very, very small distance from equilibrium. So that's the reason why we introduced the concept of D, right? So originally we have delta, and later on we have the concept of D in calculus. And it means that it is very, very small. So this is a very, I would say, conceptual idea to have this kind of small movement. But in reality, it is almost impossible to have this kind of small change. And when the minute external influence, which means that the small external influence is removed, then the process ceases. Or if the direction of the external force is reversed, then the direction of the process can be reversed. So this is the example, I would say a feature of reversible process, that when you remove the driving force, the process will stop because it is always in equilibrium. And if you want to move back, and you only need to change the direction of the force. For instance, again, back to the original example of releasing the weight, if you remove your hand, of course the weight will start to drop. However, if you keep your hand always underneath the weight, then at any moment you can push the weight back to its original position. So therefore, this is a reversible process. However, if you just release it, it will just drop, and you cannot move it back, right? So then it's a reversible process. So the distinguishment between these two is very clear. So in this section, the book is trying to mention an example of irreversible process. And if you still remember what I mentioned at the very beginning of this class, that the main goal of this chapter is to figure out what will be the maximum work that you can do, or what is the maximum work that a system can do in a regular process. So therefore, if we go back to the first page or the first slide, this delta W is very important. What is the maximum work that a system can do in either a reversible or irreversible process? So I would just say over here first that the maximum work that can be done by a system is when the system is going through a reversible process. So only when the system is going through a reversible process, we can see a maximum work. So imagine a system is changing from state A to state B, and it can do a certain amount of work. So if this process, from state A to state B is going through this path irreversibly, then the work can be done in a maximum way. However, if going through this process you have some friction and you have some irreversibility, then the work is not at its maximum. So only when you go through, or only when the system is going through the reversible process, the system can do maximum work. So this is what this section is about. Unfortunately, it doesn't state that at the very beginning, but sorry, it's 3.5. But this is what this section is about. So imagine that you have a very simple, again, a very simple system, that you have a cylinder and you have a piston that you can pull it out or push it down to change the pressure of the gas inside. And inside this chamber, you have both water and water vapor. So imagine that if the system is a closed system, such that you can absorb heat from the heat reservoir, then it is possible to, say, heat up the system, heat up the water, and then evaporate more water molecules into the upper part of this cylinder. But if the system at the very beginning is in equilibrium, then we know that there's no heat being absorbed, so everything is in equilibrium, and there are a lot of water molecules here in terms of liquid, and some of them are over here in terms of vapor, right? So you have both vapor form, and you also have the water in the liquid form. And we know that this boundary is in equilibrium, so sometimes some water will be evaporated and some will condense into liquid form, but they are in this dynamical equilibrium. And imagine that right now you can pull this piston up such that the pressure of this area or this volume has been reduced. So we know that in the case of equilibrium, we have the so-called saturated pressure, right? The saturated vapor pressure. If we suddenly move this piston up, and then the pressure of the upper part of the cylinder will be reduced, then it means that more water in the liquid part can be evaporated into the vapor part, right? Because the saturated pressure has been reduced due to the movement of this piston. And for the evaporation process, if the water needs to be evaporated into this vapor part, we know that it must absorb some heat, because evaporation is an endothermic process. So it needs the supply of heat in order to evaporate some amount of water into the vapor, which means that this heat bath, or you can say heat reservoir, will supply some certain amount of heat, Q, into the system. And then some of the water, in terms of liquid, will be evaporated into vapor. And to plot it means that, let's say, so we have, so this is the heat bath, or you can say heat reservoir, the same thing. And it's at constant temperature T. And when we move this up, so here is the water, and here we have vapor. When we move this up, the pressure is reduced. We move this up, there's a sudden reduction of pressure. Therefore, more water can be evaporated into the vapor part. But in order to perform this evaporation, the water over here needs the supply of heat, because evaporation will need to absorb heat. So therefore, the heat will be transferred from the heat bath into the system. So therefore, this system is not an isolated system. This system is a closed system, which can absorb heat from outside and also release heat to the heat bath. Okay, so this is pretty straightforward. And therefore, at equilibrium, of course, at the very beginning, like I just mentioned, the pressure over here that we enforce onto the piston is the same as the vapor pressure of the water. However, when you reduce the pressure by a certain amount, let's say P external minus delta P. So originally it's P external, and then you suddenly pull this up, and the pressure is released by a huge amount. Then the pH2O, I mean the saturated pressure, will also drop below the original saturated pressure of the water. So there's a spontaneous evaporation of water from the liquid side to the vapor side. And we know that, again, this is a endothermic process. Therefore, the heat will flow from here to here. And in that sense, the temperature of the water is less than that of the heat bath. So heat flows spontaneously from the heat reservoir into the cylinder. Okay, so this is the process that is stated. And when pH2O is reestablished as the pressure from the outside, then the evaporation will stop, and the heat flow will also stop. So only at the beginning, like when you move this up, there's a sudden change of evaporation. However, after a while, when there's a certain amount of water being evaporated into the vapor part, we know that the pressure will start to build up, and then these two sides will have well, I think these two sides will have the same I would say saturated pressure, and therefore the equilibrium will be reached. So once it's reached, then the evaporation process will stop, right? Because we know that this evaporation won't continue for an infinite long of time. Therefore, at some certain amount of time, this must stop. And this is when the equilibrium is re-established. And the heat flow will also stop, because we only need to evaporate a certain amount of water molecules. For instance, these are originally here, and when this is moved up and this part of the water is being transferred from the liquid side to the vapor side, and you supply a certain amount of Q. And once this is already here, then the equilibrium is reestablished, so you no longer need the supply of heat. Okay? So this is the reason why it says the heat flow stops once the equilibrium is reestablished. So if you consider during this process, 1 mole of the water has been evaporated, and the corresponding vapor volume is V, then the work done by the system is something like this. What does this mean? It means that over here, this part of the water molecule, in terms of vapor, has a volume of V. Let's say originally it has this water vapor part already has a certain amount of volume, right? But when you move this piston up, you also increase a certain amount of volume, and that volume has to be filled up by the evaporated water molecule, and that amount is V. So this V is actually not a, well, I won't say this is a constant. This is actually a change in terms of volume. So, but this is a notation on the textbook. But personally, I will prefer calling this like delta V. Maybe this is more straightforward to you. So imagine this is delta V. And we know that the pressure during this process, when we pull this up, it is P external minus delta P, right? So the work done by the system is this pressure times the change of volume. So the volume here is slightly different. The notation is, well, it's not very, I don't think it's very good, because in this case, the work here is, you can say this is a PDV work. So the total change of work is the pressure, which is and here it is actually the V states. So the V here, in fact, is the change of volume from the evaporation process. And another way to think of it is because when you reduce the pressure, when you pull this up, there's an increase of volume, right? So this is actually the same as the PDV work. So this is the work done by the system, because we know that it absorbs some certain amount of heat, and then this will move up, and we have some evaporation. So this is the work done by the system. And of course, you can reverse the process. So when the P external is increased suddenly, so you push this down. So now you're having P external plus delta P. Then the water pressure will increase to above the saturation, or you can say the saturated water pressure. And therefore, the vapor part will spontaneously condenses back to the liquid part. And therefore, T water is greater than T, and heat flows spontaneously from the cylinder to the heat reservoir. So here, the statement is that you have a reverse process. You have a reverse process. You push this down, and then this part of the water will be condensed, back into the liquid, And in that sense, because it's a heat releasing process, the heat of the same amount, Q, will be absorbed, will go back to the heat reservoir. And then the system will go back to its original state. Okay? It will go back to its original state. So I won't state this again. As you can see, during the reverse process, the work is done on the system because we're pushing this down. And the work done on the system is something like this because the pressure is increased by this P plus delta P suddenly. And there's a change of volume, which is V. So the PDV work will be the product of these two. So this is constant. P plus delta P is constant, and V is the change of volume of the vapor. And therefore, the permanent change in the external agency, caused by this cyclic process, is 2 delta P times V. Because at the beginning, you have this work done by the system, which is a positive number, and then you have this work done on the system, which should be a negative number, so therefore we put a negative sign over here. And if you calculate this, you'll realize that there's a net amount of work, which is 2 delta P times V. If you're not so sure, you can always draw this PV plot. And in this case, I don't have enough space. Let's see. So in this case, we have something like this. So this is the PV plot. And originally, the system is at, let's say, some certain volume. Call this V. And this is P external. So originally, it's over here. The gas molecules here is at this state. And when you when you pull this up, then the pressure drops to P minus delta P. So means that this will drop suddenly here. And we know that once you go down to this pressure, then the volume will start to grow because the vapor will start to evaporate, from the water part. And we know that that amount is, this is, I'll say V plus. So this is the volume that the textbook mentioned. But personally, I prefer delta V, as you can see, because this is the change in terms of volume. This amount of water has been evaporated, from the liquid part to the vapor part. And so eventually, we'll be over here. And if you push this piston back to original position with a larger, P external plus delta P, then it means that this will go back over here. And this is P external plus P. And eventually, the same amount of water vapor will be condensed back into the liquid part, right? So you can have this kind of cyclic process. But in reality, what we only have this line over here and this line over here. But you can imagine that there's a very sudden change in terms of pressure, for these two vertical lines. So imagine that this is a cyclic process. This is a cyclic process. Then we're making a cycle, and the piston is moving back and forth continuously. And during each cycle, the work done by the system actually is done on the system. It's the area over here. Therefore, point A over here states that the permanent change in external agency caused by the cyclic process is the work difference. And that is, so we know that this is 2 delta P, right? And this is V. So it turns out that it's the area within this cycle that gives us the, I would say, the work change. But in fact, this is just an example to tell you that the irreversible process, or you can say if there's a large delta P, you always have some certain amount of heat waste of this large. And therefore, the smaller the delta P, then the slower the process, which means that if you don't suddenly reduce the pressure, or you don't suddenly increase the pressure, you only increase the pressure gradually, for instance, using dP. If this pressure change is very, very small, then you can make sure that during the process, there's no undersaturation or supersaturation, and at each point, the system is in equilibrium with these external force. Therefore, the smaller the temperature gradient for driving the flow of heat. So when delta P is close to 0 or it's almost 0, then there will be no permanent change occurs in the external agency, and hence the cyclic process has been conducted reversibly. This means that if we have delta P approaching 0, then we know that this cyclic process will just be moving originally maybe here to here and then come back here. And then if the delta P is becoming smaller and smaller, this will be just a straight line. It will just go from here to V plus capital V, and then we will go back reversibly. And there's no this area, or the work has been converted into heat waste, and that's the thing that we don't want. So a key point over here is to state that in the case of delta P is 0, and especially when this P external means that the pressure also means that the pressure of the system, and if the system is in equilibrium at all times, then there's no this kind of, how do you say, this is the permanent change in the external agency caused by this cyclic process. So later we'll see more regarding this delta P approaching 0. And we will define like what will be the maximum work that the system can do. Okay. For the example that we just mentioned, you'll see that if it's going through a reversible process, the cycle will be very different because, like I mentioned earlier, that if it's a reversible process and it's always in equilibrium, we'll start from this point. And then we pull this up, and because it's a gradual change, so there's no big change in terms of the pressure. So the pressure is, you can say it's capped at constant. So we will just go right to this point. So essentially, if it's a reversible process, in this example, it is a constant pressure process. And because it's a constant pressure process, you can write down the first law, because say delta Q. So constant pressure, and there's a change in terms of the volume. So this is the PDV work that we want, which is the area underneath this red line. It's here. And of course, during the expansion, when the area, when the volume, the vapor is becoming greater and greater, there's a positive P delta V. So the work is positive, which means that the system is doing some work, and so it's the work done by the system. It's the work done by the system. And at the same time, there's also the heat coming from the heat bath or the heat reservoir. And you also have the change of internal energy, delta U. In the reverse process, then you go from this state and you go backwards. So since the line is the same, and the area underneath will also be the same, but since the integration is done in a reverse direction, right? So essentially, the work will still be P delta V, but it is with a minus sign. And essentially, these two will cancel out. So that's the reason why, for the cyclic process, if it's done reversibly, for constant pressure, it will just go from here to there and then come back. And the area within this, these lines will be 0. Unlike for the irreversible process that we just saw, we have a huge area being surrounded by these paths. And therefore, for the reversible process, if you go back to the original state, there's no expenditure of work, right? Because if you go from here to there and then come back, then the area is 0. But if you're doing an irreversible process, then there's a huge amount of area, depending on the irreversibility. Like if delta P is large, then of course this area is large, which means that if you want to go back to original state, you have to spend some amount of work. And that's not the case for the reversible process, because the work, the system do some work to the surrounding during the process from here to there, and when it goes back, it just needs the same amount of work to I would say, restore the original state. But that's not the case for the irreversible process, because the area is finite. Okay, the area is finite. So 3.6 is important, and it talks about how we connect the work that we're going to see, that we saw over here, to the entropy. And if you consider a reversible process, now we only consider the expansion part. So only now we only focus on the volume is becoming larger and larger. And during that process, the maximum work that can be done by the system is this P external times V, or this V, like I mentioned earlier, is the change of volume. So we can say this is delta V. So in this case, we don't have to worry about the we don't have to worry about this one, and we're no longer focusing on cyclic process. So just the process. So we start from here. And we end over here. So if the system is always kept at in equilibrium, then we know that the pressure is always the same as P external, and we have a certain amount of change in terms of volume. So the work done by the system is the area underneath. Right? And this area is P external times V. And this is the maximum work that a system can do. However, for irreversible process, we know that the pressure will drop suddenly, and then you have the expansion. Therefore, the work done by the system is only this area. So this is, I would say this area is times V, and this is, let's say, W. So this W is the case, when your system, the system that we describe over here, went through a, regular process, which is irreversible. And let's consider that the final state. So after this process, the system, let's say, it will go back to, let's restore the P external. So it will go back. Even with that, of course, the work is still the same, right? Work is still underneath, the area underneath. So the work is over here. But let's say, it will go back to the state over here. Restore the same P external. Therefore, before and after, for these two paths, this is the irreversible path, and this one is the reversible path. For both of the paths, the original state and the final state are the same. So for both cases, we start from, let's say, A, state A, and then we end up at point B. So for state A and state B, they are the same, but the paths are different. For reversible, we go from here to there. But for irreversible, we have a drop in terms of pressure, and then we have an expansion of volume, and then we go back to the state we want. So for internal energy, since it is a state function, so if the initial and the final states are the same, then the internal energy will be the same. I mean, the difference in terms of internal energy will be the same. So therefore, this is an important feature. For internal energy, for both reversible and irreversible processes, the change of internal energy will be the same. Which means that here you have, let's say, delta U is defined as UB minus UA. And for both, for both reversible and irreversible processes, delta U is the same. Okay? So based on first law, then we can write down for the reversible process, we have a subscript reverse here to make sure that this heat is the heat from the reversible process equals delta U plus the maximum work that the system can do, which is the area under this A to B, this white straight line over here. On the other hand, for the irreversible process, the heat equals the same delta U, but a different work. Because right now, for this irreversible process, the work done by the system is less than the maximum work. So in this case, this W over here is less than W max from the area that we see over here. And therefore, if you try to look at the heat, you'll see that the reversible heat is greater than the irreversible heat. What does that mean? It means that going through the same process, evolving from the same state A to state B, and if you're going through the reversible process, the heat that you absorb for the same change of delta U, for this one, if it's a reversible process, it is greater than the irreversible process. For the same change of delta U, you need to absorb some certain amount of heat, right? And for the reversible process, this heat is greater in order to change the same amount of delta U. And the reason, an intuitive way to think of this is that because due to the for the irreversible process, some amount of the work has been converted into heat. That's the reason why we cannot do maximum work. Does that make sense? Let's write it down in this way. Always go back to the first law. So we have, let me rewrite this. Plus what? W max. So since these two are the same, this one is larger than this one, so Q reverse is greater than Q irreversible. But if you want to think of it, you want to know the origin of a physical origin of why this is larger, it is because during the same during the same state change from A to B, there is some amount of work that is originally can be used to do a maximum work has been converted to heat. So let me define something called Q waste. This is not in the textbook, but this is what I typically will use to think about this paragraph. And if you can define Q waste as, say, W max minus W, then you know that this is the difference between Q reverse and Q irreversible, right? And what is Q waste? Q waste means that when the system, when the gas is expanding, there's some part of the work that cannot do the maximum work. And that part of work will be converted into waste in terms of thermal energy. And that part is heat. So you have some extra heat that's being converted from work. So therefore, you don't need that much heat to change the same internal energy difference. Anyways, if you don't know, you can probably just memorize these two lines, and then you can compare and remember that this is work max is greater than the work for the irreversible process. Therefore, this is greater. And then if you move the terms around, of course, you can end up with something like this. But I just want to emphasize that this is the waste of energy coming from the work. So if you look at the paragraph over here or on the textbook, the difference in work performed during reversible and irreversible processes equal to the mechanical energy which has been degraded to thermal energy in the cylinder. And that is this quantity I put Q waste. Or you can say this is work waste. That turns into Q waste. So originally it was mechanical energy. But due to the irreversible process, it was turned into thermal energy in terms of heat. So that amount of work has been degraded. Therefore, this equation is simply by subtracting these two, and you'll end up with the formula over here, or the equation over here. And of course, the textbook doesn't state that this is Q waste, but this is just easier for you to understand that this waste is coming from the work that's been degraded. And for a reversible vaporization process, therefore, we can define, again, the change of entropy as something like this. And you'll see that this is the delta S of reservoir. This is a very common trick that when we talk about the change of entropy, we'll discuss the change of entropy for the heat reservoir and the change of entropy for the system at the same time. And for instance, in this case, now we can get rid of this. Again, if you don't remember, always just draw something like this, like a heat bath. Or the reservoir. And here we have the system. And during this process, if it's reversible, because the heat enter the system is called Q reversed, right? And it is being drained, from the heat bath to the system. Therefore, or let's say this is a heat bath, is minus Q reverse over T. So this is at constant temperature T. And the reason why I put a minus sign here is because the heat is flowing from the heat bath into the system, right, during this vaporization process. So at the same time, you have this system, as water plus vapor. And this part has an increase of entropy because heat is entering the system. So delta as system, or you can say this is the water plus vapor. This is Q reverse over T. So if we consider the whole thing, delta as total, this heat bath plus the system as our universe, we call this total, or you can say this is universe. So during this process, we know that heat transferred from one part of the universe to the other part. And this amount is the same. Therefore, if you add these two together, it will be 0. Because if you add these two together, delta S should be 0. And therefore, no degradation will occur during a reversible process. So this is fairly straightforward, right? And you have heat coming in, and then the system will completely absorb this heat. Later, we'll see a more complicated argument for the irreversible process. But if I state it, if you still remember the Q waste, then I can probably talk about this here. And for the irreversible process, we will still have the same change of state, right? But in the irreversible process, like I mentioned earlier, we don't need that much heat to change the same amount of internal energy. Because some part of the work will be degraded, and that difference will be W max minus W. And that amount of work will be degraded into Q waste. Therefore, for an irreversible process, the heat supplied by the heat bath will be less than that for the reversible process. So a general argument is that for irreversible process, let's say maybe let's say delta S reservoir let's say it's minus Q over T. And we know that this Q is less than Q reverse. However, the system, or you can say the water plus vapor, is still Q reverse over T. Because the system goes through the same state change, right, from state A to state B. So for the system, this is still the same. But for the reservoir, since we don't need to supply that much heat, because there's some part of work will be degraded into heat to overcome this thing. Or you can say to overcome the difference between Q reverse and QE reverse. Therefore, for the heat reservoir, we only need this Q, and this Q, say Q is less than Q reverse. So eventually, if you add these two together, the total change of entropy for the whole universe for the irreversible process will be something like this. And since Q reverse is greater than Q, so this will be a positive number. So this is irreversible process. So for irreversible process, the change of entropy for the whole universe is greater than 0. In contrast, for the reversible process, for a reversible process, the entropy change is 0. The universe is still the same after you go through this reversible process. However, for irreversible process, the entropy of the universe increases. So a general statement of the second law is that the entropy of the universe, or for an isolated system, will either be 0 or greater than 0. So it's impossible to have entropy change less than 0. Either it's 0 or it's greater than 0. So this is a general statement for that. So delta S, let's say nowhere to write that down. But let's say. So this is a general statement for the second law. And total means that it's a universe, or you can say it's an isolated system. So all the heat change is within the system. Now, this system does not absorb anything from outside because this is the universe. This is the original system that we consider plus the heat bath. This whole thing has a delta S greater than 0. Okay, so the following slides will be a little bit complicated if you cannot understand this. But once you understand this, it's probably much easier for you to go through the following slides and also the paragraphs in the textbook. So here it is. For irreversible process, we define the change of entropy for the reservoir as minus Q over T. And this Q is different from the Q reverse. And for the water and vapor, which is the delta S of the system, it's this amount of change of work plus this thing. So if you still remember what I mentioned earlier, this is Q waste, right? This is the heat being degraded from mechanical work. And that difference between W max and W will be converted into heat. So as a form of waste, the thermal energy. So the system actually absorbs some certain amount of heat from the heat bath, but they also get some contribution from the degradation of work. So this is the important part over here, like this extra term. And interestingly, this is the same as Q reverse minus Q. So if you do the math, what a coincidence. This is just Q reverse over T. But of course, you can use a different way to interpret this, like I just mentioned earlier. If we want to change from state A to state B, and state A and state B, no matter what kind of path you're going through, the states, the change of the states will be the same. Therefore, of course, if we know that entropy is a state function, this should be the same as the reversible process. So it's independent of the process that you go through. That's for the system. However, if you look at the reservoir, of course, this Q is different from the Q reverse. Therefore, if you add it up, you end up with something that is greater than 0. Okay? So the entropy has been produced as a result of an irreversible process. So, the logic of all these is based on the heat waste. The heat waste coming from the degraded work over here. So that's the reason why at the very beginning of this class I emphasize on the work. We want to figure out how much work has been degraded into waste. And that's the cause of irreversibility. So if we define this Q reverse minus Q over T as the irreversible process produced entropy change, then we can rewrite the change of entropy of the system as Q over T plus this extra term, which means that we write this part from the heat waste as delta S irreversible. Okay? So now it is pretty straightforward. For the system, again, this can be divided into Q over T plus Q waste over T. And this Q waste, again, this is from the degraded work. So we can define this term over here as delta S IRR, irreversible. So this is the extra entropy change due to the irreversible process nature. And this is, of course, the heat absorbed from the heat reservoir. So these two terms should be the same. And if you add these two together, these two should cancel out, and you're left with this term. Therefore, this delta S total greater than 0 is mainly coming from the waste. Okay? This part is I think is very important. So please go back and go through this more than one time then to get a better understanding. So for a reversible process, again, it is fairly straightforward. So again, delta S total is 0, so I don't have to go through this again. I've already mentioned this earlier. And condensation, it's the same thing. I don't want to go through this again, but it's just a reverse process. So delta S system, or you can say delta S water plus vapor, is independent of whether process is conducted reversibly or irreversibly, and also independent of the process path, which means that although earlier I've already stated that entropy is actually a state function, it only depends on the initial and the final states. So it does not depend on the path. Therefore, delta S is only related to the reversible heat and the temperature. So SB minus SA, like I mentioned, from state A to state B, the evolution is from A to B, and the final minus initial, depending on its reversible or irreversible, you have this or this. But if you add these two up, it will go back to the original Q reverse over T, as I wrote over here. Okay, so no matter it is a irreversible or reversible, they all end up like this. which means that, so this is irreversible, this is reversible, which means that entropy S should be a state function, similar to the internal energy U. So as a change in entropy can be determined only by measurement of heat flow at temperature T, then entropy changes can be measured only for reversible process. In that case, the measured heat flow is Q reverse and delta SIR is 0. This states that it is very hard to identify this term experimentally. The Q waste over T, or the contribution from irreversible process, is hard to identify. So in terms of measurement, typically we want to make this process as close to reversible process as possible. So if your process is closer to reversible process, then you can, by measuring the heat being absorbed by the system, or the heat contributed by the heat reservoir, then you can identify this term more accurately. But however, it's hard to identify this thing, or this thing. So the bottom line is that when we do the measurement, we want to make sure that delta SIR is close to 0, such that the heat flow is Q reverse, and then you can determine this term more accurately. Okay, so I guess this is probably the most complicated part of this chapter. So if you can understand this part, I mean, the argument that we just went through, you won't have any problems understanding the next things that we want to discuss. So after that, we're going to look at some real case to see if we can calculate something. But if we want to calculate something again, it's similar to what I just stated for experiments. We typically focus on reversible process because then we can calculate things. Otherwise, we don't know how much waste that the system produced during the irreversible process, unless the problem tells you how much this is. So let us consider just a reversible isothermal compression of an ideal gas. So it is reversibly isothermal, which means that the temperature is kept at a constant, and we have a pressure enforced onto the system to make the volume decrease from VA to VB. So it's a decrease in terms of volume. So I guess I can remove these. And the reduction of, say, this is isothermal, and more importantly, this is reversible. And since this is isothermal, we know that it must be something like this, right? And let's say we start from VA, and we add and at VB. And it says it's an ideal gas, so that's the reason why we can have this. But we also know that the pressure will change because T is constant, so therefore the pressure will be changing as well. So this is different from what we saw earlier. Some people approach and ask about the previous example that we went through when we talk about this. This is a little bit different. In this case, we want to have a constant pressure case. Therefore, the temperature will be changing. However, in this case, the temperature is kept at a constant value. Therefore, the pressure should be changing. So you will have this kind of curve. And since this is isothermal process, we know that for A and B, so delta U, again, UB minus UA, this should be 0. The work done on this gas will be the same as the heat withdrawn from the gas. And the reason why we say this is on the gas is because we're compressing it. So we're converting work into the gas system. And the maximum work, since this is a reversible process, therefore we have maximum work. And it will be the same as Q. So if you are not familiar with this, of course, you can always start from the first law. And since this is a reversible process, we know that this is Q reverse and this is max. We don't have to write that down, but this is just for your own knowledge that this is the reversible heat and this is the maximum work. And for isothermal process, we know this is delta U is 0. Therefore, Q reverse is the same as W max. And actually, for many, most cases, I don't need to know like if this is work done on the system or done by the system. If you write down your first law like this, like I mentioned many times, that if you have a plus sign, we know that this is the work done by the system, right? So if you, after calculation, you have this as a positive number, you know that the system is doing some work, on the surroundings. However, if you have a negative number, then you know that the outside is doing the work on the system. Okay, so it depends on the convention. If you're from, I think from chemistry department, they typically use a minus sign, I don't know. Or when you learn general chemistry, maybe you have a minus sign. But please bear in mind that in this textbook, typically it uses plus sign. So next we want to calculate the work. And this is pretty straightforward because I don't think I have to write it down because it's over here. The W max is the PDV work. It's the PDV work. And we do the integration from volume A to volume B. And actually, did I write? I think this is wrong, right? Sorry. It's the opposite. Since this is a compression, let's say this. Is this correct? No? It's VA, sorry. To make sure that this is correct. Sorry about that. I should exchange these two states. So this is state A, this is state B. Because this is a compression. So if we want to calculate the work, it's a PDV work, and originally the volume A is greater, and then we reduce that to volume B. And since this is ideal gas, we can convert that to RT over V. So you end up with this RT log VB over VA. So this is RT log VB over VA. And we know that VB is less than VA, so this term should be less than 0 because this is a log. So we know that this work is a negative number. And it is pretty straightforward, right? Because the integration is done from the right-hand side to the left-hand side. So if we calculate this area using the calculus, then we're integrating this area in a reverse direction. So the number should be a negative number. So this is pretty straightforward. Therefore, since W max is less than 0, we know that the work is done on the system. Right? We define this as positive if it's done by the gas. Therefore, if it's a negative number, it means that we enforce work on the system, on the gas. The transfer of heat from the gas to the reservoir causes a change in the entropy of the gas. So the heat will be transferred from gas to the heat reservoir. So we push this down, and we do work on the gas molecules. But at the same time, because there's no change of internal energy, so there must a heat flow, from the gas to the heat reservoir. Okay, so you have a gas molecules here. You have a heat reservoir here. You're adding work to the system. The work is done on the system. But since there's no change of internal energy, you must produce heat, and the heat must be absorbed by the heat reservoir to make sure the energy conservation is obeyed. Therefore, you have a change of entropy, right? The temperature is the temperature of the heat bath, and we have this Q reverse being introduced, and that amount is the same as W max. Therefore, we also have a negative change of entropy. Remember that this is the same as, so Q reverse is the same as W max, but the change of gas, or you can say system, is Q reverse over T. And therefore, this T will be eliminated. So it's R log VB over VA. And this is, again, less than 0. So it means that this is an example. The reason why, in most of the examples in the textbook, it shows you the expansion. And the reason why we want to show compression over here is to show you that the entropy change of a system can be less than 0. Right? In this case, this is less than 0. Because we're putting energy as a format of work into the gas system. Therefore, the gas molecules are becoming more and more well-ordered, and therefore the change of entropy is less than 0. And of course, by math, you can easily see that because VB is less than VA, so this is less than 0. On the other hand, you'll see that for the reservoir, you'll get an opposite number because this is a reversible process. So the reservoir is just the minus change of entropy of gas. Therefore, we just put a minus sign in front of the change of entropy of a gas. And if you add these two together, this will be 0. Because we know that for a reversible process, the total delta S should be 0. So please bear in mind that sometimes we want to know what's the change of entropy for the reservoir. And this is a number that is greater than 0, right? Because this is negative, and you have a negative sign. So this is actually greater than 0. Which means that when we are doing work into the we're enforcing work on the system is becoming more and more well-ordered. But there must be some part of the universe is becoming more random. So, imagine that. So that's the reason why I consider world peace is impossible. There are some parts becoming more and more peaceful, but there must be some part of the world becoming more and more chaotic. Okay, like U.S., they're getting better and better, but some part of the world is getting worse and worse. So this is because we're enforcing this work onto the system. But you must drive the heat to the outside world. And in this case, the surrounding is the reservoir, and you are dumping heat into the reservoir. Therefore, the heat reservoir is becoming more and more, I would say, more random or becoming more chaotic. But the work is done on the system. Therefore, the gas, this part, is becoming more and more well-ordered. But if you look at the whole universe, the whole thing, the delta S total is 0. And for the opposite operation, that is the expansion. For the expansion, it's the opposite flow of Q. So the heat is flowing into the system, and the system will be doing work to the outside because you're expanding the gas, from here to here. Sorry. Therefore, you will have the larger, the change of the gas entropy will be greater than 0, and the reservoir will have a change of entropy that is less than 0. So that's the opposite operation. So I think I'll stop over here. Then we'll talk about adiabatic process. Have PA to TA, and then PA and TA for the initial state, and later it's evolved into PB and TB. And although this is not very necessary, but of course we can plot this on the PV plot. And right now we're talking about, this is expansion. Okay, so this is an expansion process as a very usual example, adiabatic. So we have here, and maybe we end up something like this. So this is PA. And here we have okay, something like this. And we know that the constraint is that PV to the gamma is a constant. So for adiabatic process, we know that the final state will end up at some certain temperature, TB. For irreversible process, although the line can be something similar, but eventually, we'll see that the irreversible process will give you a greater final temperature. So for a given decrease in pressure, the more irreversible the process is, then the more heat will be produced in the gas by degradation. Therefore, the final temperature will be higher, as well as the internal energy will be higher, and there will be a greater increase in entropy. So we already know that for adiabatic process, let's say this Q is 0. By Q is 0, we mean Q reverse is 0, and therefore delta S of the gas, let's say, is Q reverse over T. This should be 0. So from state A to state B, B, this is 0. However, if you're dealing with an irreversible process, also this is reversible. we know that there must be an increase of entropy. If you still have that in mind, what is that? Q over T plus, this is something like this, right? So if irreversible, we still have this term. Although Q is 0, but you still have this thing. Q is 0, but delta as gas, this is irreversible, is Q over T plus the irreversible part. Therefore, gas irreversible will have this extra term coming from the irreversibility. So it's greater than 0. Well, for reversible adiabatic process, it should be 0. And because of this, we know that there must be a change and a degradation of work into heat. And that will further heat up the gas. Therefore, when you go from state A to state B, the temperature will actually become higher than the adiabatic reversible process. So that is the reason why it states here that the more heat will be produced in the gas by degradation, therefore the higher the final temperature and also the internal energy. So I don't know how to draw it, but we know that anyways, the temperature will be higher in this case, as well as the internal energy. So this entropy is originating from the irreversible process, as I stated over here. So with these concepts in mind, we'll switch gear to talk about heat engines. So as I mentioned at the beginning of the semester, that heat engine is the heart of the second law of thermodynamics. And heat engine is a device which converts heat into work. And during the operation, some quantity of heat is withdrawn from a high temperature heat reservoir, and some of the heat is converted to work, and the remainder will be transferred to the low temperature part of the heat reservoir. So here is a schematic illustration. There are a lot of different kinds of illustration to show you how the heat engine will work. And there are some mechanical things that will do work over here, but always bear in mind that you need a heat reservoir and a heat reservoir at lower temperature to drain the heat and to supply the heat. And therefore, based on the conservation of energy, we know that Q1 plus W will be Q2, right? Because imagine there's no heat waste, and there's from the conservation of energy, we know that the sum of these two should be equal to this one. And an example will be the steam engine, that you have the supply of gas, maybe with a higher temperature, and it will expand and then push the piston. And once it was cooled down, something mechanical will push this back to allow the heat gas, harder gas to come in again and then to expand this. So it can continue to form this cyclic process. So the piston will move back and forth and to drive the wheel. But at the same time, this wheel will push this piston back to make sure that it can form this cyclic process. So this is just an example of what a heat engine or steam engine should look like. But conceptually, if you don't want to think about engine that much, you can always just define the efficiency of a heat engine represented by eta over here. And eta is the work obtained over the heat input. So this is an important definition of efficiency. So for many different kinds of tools, we will define the efficiency like this. So the work is something that we can do, useful things, to make things in order. And the heat is something that is random and that is drained, it's being sourced from the hotter part of the heat reservoir. Therefore, it's represented by Q2 over here. If you still remember, it is this term. So W over Q2 is the original definition of the efficiency. But based on the conservation of energy, we know that this W is Q2 minus Q1. It's a difference between the heat, getting from the hotter part, and the heat that is being drained, to the cold reservoir. So if you know this, then it can be simplified. The efficiency can be simplified to 1 minus the ratio between Q1 and Q2. So you can imagine that if you can reduce Q1 to, say, 0, and then increase Q2 to infinity, then the efficiency will be close to 1. Right? If you can reduce this part, which is a form of, I would say, like a waste. If you can reduce this part and then increase, this to be similar to the work, then the efficiency will be close to 1. And that will be the maximum efficiency, which is 100%. And one of the examples, I think the most important examples that probably you've already learned in the first year when you talk about general physics and general chemistry, is the Carnot cycle. And the Carnot cycle consists of 4 different processes to form a cyclic process. So at the very beginning, you have the isothermal expansion, and it is a reversible process. So from now on, a lot of things that we discuss will be, especially when we talk about the PV plot, and anything that's on PV plot, most of the time will be reversible process. And there's an isothermal expansion at a higher temperature. So here, from A to B, you have this isothermal expansion at temperature T2. I'm not sure why in this textbook it uses this small t, but just bear in mind that this means the temperature is at a higher temperature T2. And once it reaches some certain point, it will go through an adiabatic expansion. So the adiabatic expansion means that there's no heat will be absorbed by the system, but at the same time, it is still doing some work, because you can see that it is expansion of gas. Therefore, the system is doing work to the outside. Once it reaches this point, C, it will go back isothermally. So here is another isothermal process, and it's a reversible compression from state C to state D. So the volume of the gas is being compressed. And then later, you will go through another adiabatic compression to go back to original state. So in short, you can decompose the cycle into these 4 different processes, and I don't want to go through these paragraphs, but the bottom line is that for A to B, we're absorbing heat
from the hot end of the reservoir. So if we draw the heat engine out, it's something like this. So this is T2, T1, T2 greater than T1, of course. So Q, say Q2, this is Q1, this is work, and this is Carnot engine or Carnot cycle. During the first part from A to B, Q2 from the heat reservoir at T2 is added to the system, to the system of gas, and performing work W1. And this is not the total W that we want. This is only during the first part of the process you have W1. So we know that this is the sum of first W1, and during the second process you have W2. And at that time, there's no heat being transferred into the engine because that's an adiabatic process. And then you have from C to D, you dump the heat into the other reservoir at temperature T1. So that's this process. And you also have to do some work. And then later you have the compression. So this is compression, this is also compression. So you'll see that for these two, this is A, B. I don't want to write this, but this is positive, and this is negative, and this is negative. Right? So there's no problem with these things. Because although it states that it's the area, but we're going backwards. So for C to D and D to A, the work will be negative. So in order to calculate the efficiency, we know that the efficiency is work over Q2. So if we can calculate all these, and we also know Q2. Q2 is a number that we defined at the very beginning, then we can estimate how large this efficiency will be. So through the textbook, they try to estimate how large. It tries to estimate how large this area is within this cycle. So the work done for the Carnot cycle will be the area within this cyclic process. And we know that the total Q will be Q2 minus Q1, but it doesn't really matter at this point because what we want is Q2 at this point. And another key point is that for the cyclic process, delta U is 0 because we went back to the original state. So we go from A, and then we start from A, and then we end up at state A as well. So there's no state change in terms of internal energy. So delta U is 0. Therefore, we know that W is the same as Q. Okay, this one is the same as this one. And I've already stated this over here, in the previous slide, so I don't want to state that again. So right now, I think what Carnot stated when he used this engine to describe thermodynamics is that there's no engine that has a greater efficiency while compared to the Carnot cycle or the Carnot engine. And to prove that this is real, we have to use some assumptions. So assume that you can get some heat engine that will possess greater efficiency. So imagine that this is the efficiency you have, and you want to have a larger efficiency than this one. So let's say this is so imagine that you have a heat engine that has an efficiency greater than this number. How can we do that? The first thing is, this is the original heat engine. And the first thing that we can do is we reduce the amount of heat waste and increase the work. So imagine that you have an engine that is better than Carnot engine that can produce more work and reduce the amount of heat waste that's being dumped into the cold reservoir. So in that case, this work W prime is greater than the original W. And Q1 prime is less than Q1. So in that case, you have, we will say this is Q1 Q2. And since this Q1 prime is less than Q1, so this number is greater than this, right? So imagine that you have that kind of engine. And another example is that perhaps the work is the same. But what if we can reduce both Q2 prime and Q1 prime? In that sense, we're reducing these two things. We reduce the heat that's being absorbed by the mechanical part of the heat engine. At the same time, we're reducing the waste, and the work is still the same. So in that case, you have something like this. And this is smaller than Q2. This is smaller than Q1. And in that case, you will also get a larger efficiency. Or you will also get a larger efficiency. This is because imagine that originally, for example, you have 1 minus, say, let's say 4/5. And if you can have a heat engine, so this is 1/5. And if you can have a heat engine that is, say, 2/3, then you have a larger efficiency, right? This is larger. Oh, sorry, this is larger. So if you can reduce the heat of Q2 and the same as for Q1, then you can increase the efficiency. So there are two ways to increase the efficiency from the original ideal Carnot engine. So right now, we already have these two imaginary heat engine that is having efficiency that is greater than Carnot cycle. However, if we reverse the first thing, the original engine, and then combine that with this one, which is more energy efficient than Carnot cycle, then we'll start to see something weird. This is the first one, but it is running in reverse. Okay, so this is still the Carnot engine. But for the second one, we know that Q1 prime is less than Q, and W prime is greater than W. So if we add these two together, if we put this imaginary engine with the original Carnot engine, if we put this together, then we'll end up with something like this. Since Q2 are the same, so these two will cancel out. And you end up with no heat being transferred to T2. On the other hand, over here you have Q1 minus Q1 prime, and over here you have, W prime minus W. And we know that this is a positive number, right? Because we already state that W prime is larger than W. And also Q1 prime is less than Q1. So these two terms are positive numbers. It means that you have an engine that can pump heat to do work without dumping anything to somewhere else. So this is Thomson's statement, or you can say Kelvin's statement on the impossibility of having heat engine like this. So in this case, if you have a heat engine with efficiency that surpasses Carnot cycle, then you can create a heat engine like this, and this is this is not consistent with Thomson's statement of the impossibility of having an engine that can pump heat and directly transfer that into work. So this is, let's say, Thomson's heat engine that you completely convert heat into work. And this is impossible. This is impossible. Therefore, we know that we cannot create a heat engine that is having efficiency greater than Carnot cycle. Since this is impossible, therefore, let's say, so by playing with a combination of engines, we see that the imaginary engine 2 is not possible. Therefore, we cannot have an engine that is having efficiency greater than the Carnot engine. So this is the first proof. And for the second one, for the third one, we'll do the same thing. And this is Clausius' statement that if you combine the original Carnot cycle engine or Carnot engine with the third one, then you will end up with something like this, because the work is the same. So these two will cancel out. Therefore, you have no work being sent into the mechanical part, but at the same time, you have heat flow coming from the low temperature part flowing into the high temperature part. So this is Clausius' picture that this is not possible. You have an engine, but this engine is not doing anything, which means that the heat will just directly flow from the low temperature part of the universe to high temperature part of the universe, which is impossible. This is not possible to happen. Therefore, engine 3 is not possible. So again, we show that trying to have a heat engine with an efficiency that surpasses that of Carnot cycle or Carnot engine will be, will violate the statement being proposed by Thomson and Clausius. So this was what I put in the very beginning of the semester from the book of Peter Atkins, that the principle of Thomson is that it is impossible by means of cyclic process to take heat from a reservoir and convert it to work without transferring heat to a cold reservoir. You always need to dump something into heat reservoir. And we know that right now that these two are the same. They are all consistent with the definition of Carnot engine, that there's a maximum efficiency that an engine can have. And for the principle of Clausius, again, it is impossible to transfer heat from cold to hot reservoir without converting certain amount of work to heat. It's impossible to do this. So these two statements are the same, and they are all stating, they all come to the same conclusion that these imaginary engines with larger efficiencies are not possible. So you can say that these two statements are equivalent to stating that Carnot cycle or Carnot engine has the maximum efficiency that all heat engine can have. So therefore, it's important to figure out what is the maximum efficiency that this engine, Carnot cycle, can give us, and how to quantify that. So we know that efficiency can be written as something like this. And this is a function of temperature. Because all we know about a heat engine is the temperature over here. So whatever is going on inside should be able to be calculated by just knowing the temperature of the heat reservoir and the cold reservoir. So once we know these two, we should be able to come up with something that determines the efficiency of the heat engine, or at least for the Carnot cycle. So we can define this efficiency as a function of temperature. And in this case, we know that it's a T1 and T2, so we define that as a function of T1 and T2. And it should be, again, this can be simplified into this. Or we can say, since this is 1 over here, we can say the function, Q1 over Q2 should be a function of T1 and T2. And imagine that we can have this kind of cycle, and they can be divided into, this one can be divided into 2 cycles. So imagine that we have T1 and T3. So if we undergo this kind of process, we can divide that cycle into one like this and one like this, and add them together. Therefore, if we consider a cycle with T1 and T3 in between them, and this should be the combination of T1 and T2 and T2 and T3 cycle. So we also know that the function, Q1 over Q2 is a function of T1 and T2, and that will be the same for the other cycle, which involves Q2 and Q3. And therefore, for Q1 and Q3, again, it's a function of T1 and T3, but we also know that if you time these two together, Q1 and Q3, this third line and the second line together, you can retrieve the original Q1 over Q2. Therefore, the function of T1, T3 over function of T2 and T3 should be a function of T1 and T2. It means that it's better like if function, this function of say T1 and T3 is better something like, can be decomposed into something like this. Or you can say so it depends. As long as it's some kind of product. And we know that the inverse is also a kind of product. right? So we know that due to this relation, this function should be able to be decomposed into something like this. And that will be the same for a function of T2 and T3. They should be able to be decomposed such that when they put together, they will cancel out and they will be reduced to the function of T1 and T2, and in the same format. So the argument here is very straightforward, that since what I just mentioned, the function is better to be something like this. It can be decomposed into the function of T1 and T3 separately. And that will be the same for T2, T3. Therefore, the efficiency function, which is related to T1 and T2, should be the ratio of a function of T1 and T2 alone. So we come up with this idea that Q1 over Q2 should be the function of T1, temperature 1, over the function of temperature 2. And the simplest and the possible form, which is proposed by Kelvin, is that why not we just use temperature? And later we'll see that this is actually correlated to the definition of entropy. And right now we'll see that we put Q1 over Q2 as the ratio between temperatures, because originally it's a function of temperatures, but right now we use the temperature. And therefore, this ratio, which defines the efficiency, should be T2 minus T1 over T2. And eventually, if you want to just memorize this, which is fine, then the efficiency is simply, again, from the definition and from the conservation of energy, and from the argument that we just went through, so function of T1, function of T2, and eventually Kelvin proposed that this is simply just temperature, although we don't know what temperature this is. Eventually we'll know that this is the reason why we call this Kelvin scale for the absolute temperature is because eventually we'll see that this is where this temperature scale is defined or is defined from. Therefore, eventually for this heat engine, you have this and this. So once the temperature of the heat reservoir and the cold reservoir are defined, then the efficiency, the maximum efficiency based on Carnot cycle is also defined. And I believe that I mentioned this at the very beginning of the semester. So some notes. This defines the temperature scale that I mentioned. Define the zero of a temperature scale as the temperature of the cold reservoir, which makes the Carnot cycle 100% efficiency. So if T1 goes to 0, as I mentioned earlier, then the efficiency is close to 100%, right? If T1 is approaching 0, then efficiency is 100%. So the way for classical thermodynamics to define the absolute zero is from the efficiency of heat engine. When the temperature of the cold end or the temperature of the cold reservoir is 0, then we will have maximum efficiency, which is 100%. And equation 3.6, which is this one, defines an absolute thermodynamic scale of temperature. And that is independent of the working substance. So whatever heat engines you have, the maximum efficiency is very well defined, and it is related to this ratio. So this will give us a very good definition of the absolute temperature scale. And it is independent of the working substance or working materials or whatever gas you put into your heat engine. So let us consider just 1 mole of ideal gas. And here we wanted to derive the explicit form of this. And remember that the argument that I just went through seems like there's no involvement of detailed calculation. I just stated that due to the cyclic process, the nature of cyclic process, we should have function like this. And Kelvin proposed that we should define f of t like this. But in reality, actually, we can go through detailed calculations and then show that explicitly that the efficiency is indeed 1 minus T1 over T2. And to do that, we go back to, we assume there's a very simple system, which is ideal gas, and only 1 mole. And we will go through this Carnot cycle a step at a time. And from the process, maybe I should plot it here. So again, we have the PV plot of Carnot cycle. Typically, it's something like this: A, B, C, D. So the process is like this. So from A to B, it's a reversible isothermal expansion at temperature T2. Isothermal, so we don't have to worry about temperature. And also delta U is 0. And here we know that Q is 0. So there are some constraints that you can already put on, to the PV plot to make sure that you know like what's going on. First of all, delta U is 0. Then the heat, being absorbed, from the heat reservoir that will do the work will be the same. So W1 is actually equals like Q2, and it's RT2 log VB over VA. And remember, we've already done the isothermal expansion calculation before. So for isothermal expansion of ideal gas of 1 mole, we know that it's Q2 over here, and here, let's say we have Q1. Q2 over here is W1, it is RT log VB over VA. And VB is the volume over here, and VA is the volume of the original state. And we know that this is a positive number, right? This is greater than 0. Now this is and from B to C, it's a reversible adiabatic process, and it's also expansion for adiabatic process. Q is 0. Therefore, the work is the minus of the change of the internal energy. And here we use the feature of ideal gas that du for the adiabatic expansion Q is 0, therefore W2, which is the process from B to C, is the minus of change of internal energy, right? This is because Q is 0. Q is 0. And therefore, this can be calculated by minus CV dt. And we know that the temperature is from T2 to T1. From here to here. So here we have T2, here we have T1. Whoa. So the bottom line is that this is a negative number. This is a inside the integral. This is a positive. This is a negative number. So with a minus sign, this is a positive number. So W2 is also positive. So now we know that from here to here, you have two positive numbers in terms of work. These two. And so for the rest, for the compression, you do the same thing. Then you have two negative numbers, W3 and W4. So the total work done by the gas, which is the area inside this cycle, will be the sum of these four works. And if you add them up, it will be something like this. And it turns out that there are some terms that will cancel out immediately, right? This term and this term are the same, which means that along these two paths, the work done are the same. So they will cancel out. So you end up with RT2 log VB over VA and RT1 log VD over VC. And there's some math, based on the nature of ideal gas, that you'll see that VB over VA is VC over VD. So you can summarize these two together. And the heat absorbed from the heat reservoir is simply Q2. So it's not related to Q1 at all. So the efficiency, if you put it that way, if you simplify that, it turns out to be T2 minus T1 over T2, which is the same as what we assumed earlier, okay, by Kelvin's definition of function of T. So actually, the hardest part is to summarize, is to show that VB over VA is VC over VD, and use the law of ideal gas to convert that ratio to the temperature, which maybe next time I'll go more in details, but if you want, you can go through that. It's also in the textbook. So eventually, we have the Carnot cycle efficiency like this. So I guess I'll stop over here, and next week we will talk about more on the second law of thermodynamics.